Greeting guys. So today I'm going to take you to the deep journey into vision language models, ending with how they work and why they have been become one of the foundations in modern AI research and real world applications. To start with, traditional AI systems treated perception and reasoning as separate models, say a vision model for images and NLP model for text. So early system which learned to tag images with classes or rules but offered no semantics beyond those discrete labels. And language models, on the other hand, learn to reason about text, to describe abstract topics, answer questions, and also follow instructions, but were blind. So the question that motivates the rise of VLM was, can we build system that can resonate about what they see in the same conceptual space in which they understand text? So the answer after years of research turns out to be yes. And the result is what we call vision language models. So at their core, VLMs unify perception and language by translating the visual information into a shared representational space with text. So allowing a single model to reason about both modalities jointly. So this goes beyond captioning or classification. So it enables models to generate rich explanation, answer questions about the image, and also perform tasks that require both perceptual grounding and linguistic reasoning. So let's unpack this deeply, starting with the architectural foundations. So let's discuss about the foundation of VLM architecture. So vision language models are typically consist of three major components. So one is a vision encoder, and the second one is a multimodal fusion mechanism, and the third one is language decoder or generator. So the vision encoder, which often a vision transformers, which is VIT, which takes the raw pixels and convert them into a sequence of embeddings or tokens. So instead of processing the entire images as pixel matrices, transformers partition the images into patches. That is 16 into 16 or 32 into 32. And then project these into a latent space where each patches become a token. So the choice of transformer here is critical because it allows the architecture to use attention mechanism that can capture long range dependencies across the image, to how token interactions works in languages. So these visual tokens are then fed into a fusion mechanism that aligns them with textual tokens. So early work used the contrastive learning objectives to create joint embeddings. That is, the example is clip, where the images and text that match sit close in the embedding space. Later, advances moved towards generative multimodal models. So where the alignment is learned end to end through cross entropy generative laws rather than contrastive learning or contrastive objectives. So enabling direct text generation from the vision inputs. So this trend from contrastive to generative and reasoning oriented paradigms is one of the major macro shift observed in over 26,000 survey papers in this area spanning from 2023 to 25. So once visual and textual tokens are in the same representational space, the language model, which is typically a decoder-only transformer or hybrid encoder-decoder, uses a cross-attention layers to integrate both modalities and produce natural language outputs. So the model thus predicts the next word conditioned on visual context, just as it would predict the next word conditioned on prior text, enabling the rich descriptions and then visual question answering and even the interactive visual reasoning. Let's discuss about the VLM trainings. So in the early wave of VLM research, training was dominated by contrastive objectives, where the model learned to associate the images and captions in the embedding space. But a major trend, clearly documented in extensive literature, is that modern VLMs increasingly adopt instructive tuning and then a generative pre-training objectives. So these allows the models to follow vision conditioned instructions and generate text, reframing the perception problems as multimodal sequence modeling rather than the discriminative classifications. So also additionally surveys highlight that training practices have shifted from building multimodal encoders from scratch to like fine tuning strong pre-trained backbones with adapters or lightweight bridges. Like parameter efficient adoption methods such as like LoRa adapters and like prompt tuning have become like mainstream, allowing even the large models to be efficiently aligned to vision modalities without like retraining everything. So let's discuss about the several distinct training paradigms in the literature. So one is like single stage tuning, like where vision and language models are jointly pre-trained. And then the second is like two-stage tuning, where the vision encoders are pre-trained on a large image corpora before like being integrated with a language model. And the third one is direct adaptation. So where like pre-trained language models are adapted to like vision task using parameter efficient techniques. So let's discuss about the multimodal fusion. So multimodal fusion is the mechanism by which like visual and text representations are combined. So it's essential to VLM capabilities. So research classifies like major fusion strategies into like three categories. One is like encoder decoder framework, where like separate encoders generate modality specific embeddings that are later integrated. And then the second one is attention based fusions, where like cross attention layers are dynamically bind visual and text informations. And the third one is like graph neural networks in some robotics or 3D contexts where the spatial structure is explicit. So let's discuss about the current state of thought models. Like by 2026, the VLM landscape covers a spectrum from like compact model optimized for edge devices to massive like multimodal systems for general reasoning. So starting with like Gemma 3 from Google, which uses a large decoder model, decoder only transformer with a high resolution visual context window and then grouped query attentions, enabling like long context multimodal reasoning. And then Quant 2.5 Omni and similar multimodals, which combine powerful text generation with robust vision integration, often paired with like specialized reasoning heads. And then model like mini CPMV and intern VL variants shows that specialized optimizations, which matters for like tasks like OCR and detailed scene understanding. The key insight from more recent analysis is that scale alone is not the dominant factor in vision performance. Instead, how an encoder is trained and its loss functions, resolution handling, and then the supervision signals often matters more than a sheer parameter counts. For example, smaller encoder trained with geometry aware losses can outperform much larger models on many tasks. That just challenging the intuition that bigger always means better in multimodal AI. So in terms of like benchmark and evaluation, unlike a simple accuracy score for classification, VLMs are like evaluated on diverse metrics including CIDR for captioning and reasoning consistency measures and robustness benchmarks that test how model handle cultural or contextual variations in images. Why VLMs are transformative? Like vision language models are reshaping the like perception in AI instead of like treating vision as standalone descriptive problem, like classify, detect, and segment. Like VLMs treat it as an information stream that like integrated into a reasoning pipeline that enables like semantic understanding of complex scenes and also instruction based visual task, which is like describe the person's emotions, and then like generalization beyond like fixed label spaces, and also like zero shot transfer to like novel task. Also, like research survey confirms that this shift, like reframing the perception as instruction following, is one of the major macro like trend. So diving the multimodal research. So this transition has like profound practical implication in robotics. Like VLMs are being used for like object manipulations, navigation, and SLAM by like providing rich semantic context in medical imaging. They support like cross-modal interpretation and report generation, and then in human machine interaction, they form the backbone of multimodal agents capable for interpreting and generating the natural guidance based on the visions. So let's go and discuss about the practical insights from like research to deployment. So we have just developed a demo application. So let me walk you through the code sample, a live demo. Like we are going to like build a real-time vision language application. So what this application does is very simple, but it can be applied in real time. So it will like open your computer camera and then capture the frames from the camera and then sends those frames to your local vision language model, and then AI will like describe what it sees in the real time. So basically, we are building a local AI that can look at your camera and explains the scenes. And the best part is that everything runs locally using Apple MLX and the small VLM model. So basically, you see here in the code, we have two modules, which is app NumPy and then index HTML. So first, let's look at the Python backend. So this parts like handles like loading the AI model, like receiving the images from the browser and running the model inference and then sending back the description. So first we import all the necessary models here. So and then we have like MXVLM models as well. So these functions which allows us to like load the model, format the prompts, and generate the text description from the images. And then we are like initializing the Flask server here. It just simply creates the web application, and then we are like selecting the AI model here. So as I said, we will be using small VLM vision language model, which is lightweight, optimized for MLX and quantized to like 4-bit, so it runs faster. And then in order to like prevent the overlapping inference, we have created the global lock, which is very important here. If multiple camera frames arise at the same time, the model might like start multiple inference processes, which can like slow down everything. So this lock ensures that like only one inference runs at a time. So if the model is like busy, the request simply returns thinking. And then we will be loading the model. So here this loads the vision language model, the processor, and the model configurations. So this only happens once when the server starts, so inference become faster afterwards. And then this is the home page route. So this simply like loads the HTML page that contains the camera interface. And we have our image analysis API. So now like comes the main part, like the analyze endpoint, which this will routes like the received images from the browser. And again, we are just checking if the model is busy, if another request is already running. So we skip the new frame, and this helps in keeping the system fast and responsive. And once the image is received, we'll be like converting or decoding the image. What happens here is the browser sends the image as base 64 and we decode it and then convert it into a PIL image and then make sure that it's RGB format. And then we will be creating this simple prompt here as described what you see. And then we have our apply chat template, which will propose the prompt in the format expected by the vision language model. And finally, here we have the generate method, which just generate the response actually. So here we give the model the prompt, the image, and then the token limit. I just put it like 48 to make it faster. Feel free to like play with this parameter. And we keep the token limit like small so the response is fast. And returning the result, finally here we send the result back to the browser. And in the main, like we will be starting the server on the port 8080. Now let's look at the front end, which is inside the templates folder. So it just opens your camera and captures the frame and send them to the AI server. So we use the like a browser camera API. So here we use the browser camera API. So this has permission to use the webcam, and if allowed, the video stream appears in the video element. And we use an hidden canvas. So this copies a frame from the video into the canvas. So then we convert it into an image. And then we will be sending the image to the server via fetch. So every frame like gets sent to the A model. And when the server responds, we update the captions. So the UI will display the live AI description. And finally, we will be setting the interval here to 300 milliseconds. So the AI updates roughly 3 times per second. It will update the result in the interface 3 times per second. So basically, if you see the overall pipeline is from camera to capturing the frame and then send it to the Flask API, and then it will be calling the vision language model, and then it will generate the caption and then display the result. So let's run the application. So what you're seeing on the screen right now is not a cloud service, not an API call. So this is the vision language model running entirely locally on a consumer laptop. So using a live camera feed and producing a natural language descriptions of the visual scenes in near real time. I want to use this demo to explain not just what the system does, but how it works internally, why it is architect this way, and what trade-off we are making from research and engineering perspective. Let me start by clarifying something important. This system is not performing like traditional computer vision. It is not detecting bounding boxes. It is not classifying the objects into a fixed taxonomy, and it is not tracking the pixel frame by frame. Instead, it is doing something fundamentally different. It is reasoning about visual inputs using a language model. So that distinction is critical because it explains both the strengths and the limitations of what you are seeing. At a high level, the system has four layers. The first layer is perception, which begins with the camera. The browser captures frames from the webcam and periodically samples them. Importantly, we do not process video continuously at 30 frames per second. So that would be neither computationally feasible nor conceptually correct for this kind of model. So instead we treat each frame as a snapshot of the world, and then similar to how a human might glance at a scene, pause and then describe what they see. So once the frame is captured, it is resized and compressed directly in the browser. So this is a deliberate design choice. Vision language models are sensitive to input resolution, but beyond a certain point, higher resolution does not yield better semantic understanding. So it only increases the latency. By standardizing the input into a fixed resolution, we ensure predictable inference time and stable memory usage. The compressed image is then sent to a local backend via a lightweight HTTP request. There is no cloud involved here. The Flask server is running on the same machine, and the image never leaves the device. This is important for both the privacy and a system design perspective. So, in many real world applications, healthcare, robotics, assistive technologies, sending camera data to the cloud is either undesirable or unacceptable. So, once the image reaches the backend, it is decoded into a standard image representation and passed to the vision language model. So, this is where the most interesting part of the system begins. The model we are using is SmolVLM, so which is a compact instruction-tuned vision language model, which is designed for efficiency. Architecturally, it follows the now standard pattern used in modern VLM research. The image is first processed by the vision encoder, which is typically a vision transformer. This encoder does not see objects in a symbolic sense, so instead it converts the image into a sequence of visual embeddings, what we often call visual tokens. So each visual token represents a patch of images, and through the self-attention, these token captures the spatial relationship and contextual dependencies. Importantly, at this stage, there is no language involved. The model is purely operating in the latent numerical space learned from data. So these visual tokens are then projected into the token space of a language model. So this projection step is like critical and is a result of extensive research in multimodal alignment. Once projected, the visual tokens are indistinguishable, like from the language model's perspective, from textual context tokens. So they become part of the same sequence. So this is a key conceptual leap behind like vision language models. So the language model does not need to like understand visions explicitly. It only needs all reasonings, semantic interpretation, abstraction, explanation happens inside the language model. So in our demo, once the visual tokens are embedded into a language model context, we provide a short instruction prompt such as like describe what you see. So this prompt is not just a convenience, so it reflects how these models are trained. And then modern vision language models are instruction tuned, meaning that they have been like exposed during training to large data sets where images are paired with natural language instruction and responses. So these allows the same model to perform many tasks simply by changing the prompt. So when the inference begins, the language model generates text autoregressively, token by token. So this process is inherently like sequential and computationally expensive. Each generated token like depends on all the previous tokens as well as the visual context. This is why inference takes seconds rather than milliseconds, and why we must carefully manage how often we call the model. So you may notice that the caption does not update continuously. Instead, it updates periodically. And sometimes you see a brief thinking indicator. This is not a bug. It reflects a deliberate like concurrency control mechanism. We allow only one inference to run at a time. So if a new frame arrives, so while the model is still generating a response, that frame is dropped. This avoids like overlapping GPUs or like accelerated workloads, which can cause instability or crashes. So particularly on consumer hardware using unified memory architecture. So this design choice also like reflects a deeper insights from human perception. Humans do not like continuously narrate every frames of visual input. We observe, interpret, and then speak. By limiting the inference frequently, we align the system more closely with how perception and the language works together in the natural cognition. So now let's talk about latency because this is often the first concern people raise. Like on the laptop class device, a single like inference may take several seconds. So this is not like because the model is inefficient, but because it is performing a full reasoning pass over a high dimensional multimodal context. So each output sentence like represent thousands of internal operations, attention computations, matrix multiplication, and probability evaluation. So to make this usable in a live demo, we apply several optimization. We limit the maximum like number of tokens the model can generate, and then this bounds the inference time and prevents overly verbose responses. So we also reuse the same model instance across requests, like keeping it warm in memory. And quantization further like reduces memory footprints and computational cost, allowing the model to like run efficiently on Apple MLX backend. And despite like these optimization, this is still not like real time in traditional computer vision sense. But that is not the goal. The goal is like semantic real time, providing timely, meaningful description that help a human understand SE. Like from that perspective, a response every few seconds is often more useful than a noisy stream of low level detection. From the research standpoint, like this demo illustrate a broad trend in AI system design. We are like moving away from like pipeline composed of many specialized model like detectors, trackers, classifiers, role engine towards unified model that operates in a shared representational space. So where the vision language models act as a semantic interface between the physical world and symbolic reason. So these are of course the limitation. The model can like hallucinate details. So it may like infer things that are not strictly visible. So it may struggle with fine-grained spatial reasoning or precise counting. So these are like active research problems, and they arise from the fact that the model is trained to generate likely language, not verified truth. Like understanding and mitigating these failures more is one of the central challenge in multimodal AI research today. And however, like even with these limitations, system like this represent a significant step forward. Like these allows us to like build interfaces where like machines can explain what they perceive and justify their interpretation and interact with human using the natural language grounded in sensory input. So, to conclude, this demo is not just a technical showcase, it is an example of a larger shift in artificial intelligence from like system that sees or speak to system that see and explain. Running this locally on a consumer hardware demonstrate that this shift is not confined to like large data centers. It is becoming accessible, deployable, and practical. So that's it. So in this tutorial, we saw what is vision language model and its foundation of VLM architecture and how VLM training works. And also we build a real-time vision AI application using small VLM and Flask. So this kind of setup like can be used in many real-time applications like smart accessibility tools and AI-powered monitoring systems and in robotics visions and also in real-time scene understanding or even in interactive AI assistant. And since the model is like lightweight, it can run efficiently on modern Apple Silicon machines using MLX. I hope this tutorial helped you understand how vision language models can be integrated into real-time application. So if you enjoyed this video, feel free to like, subscribe and share. And I will see you in the next tutorial where we explore more practical AI and machine learning projects. Other than this is Abunya. Bye for now. Thanks for watching.